Okay, great. Well, thank you for coming again. I hope this time you don't freeze. Last time was a bit challenging for that. But okay. So this for me is a kind of more important one of the lectures because it's kind of the transition between the, let's say, the older papers around between 98 and 2002, something like that, to kind of the newer results. So the idea is to first finish setting up the spectrum and then getting the correlator, mainly the new results, which are the correlators in the spectral flow sector. So last time what we did is we started with, working with the Euclidean model. Recap requested by Ricardo. So with the Euclidean model, which is the coset model on H3+, which is just Euclidean AdS3. And then we said that here we looked at the normalizable spectrum, but the normalizable states. They come in two kinds: the continuous representations, which are states which belong to this, which are denoted usually like this, where the hat is for the affine module, right? And the basic idea, and the discrete states look like this, which come in the version of highest weight states with the minus, or lowest weight states with the plus. And so the basic idea is that I start from some states which are like this, which satisfy that J, for any J for a mode positive on the primary state, I get 0. For the 3, for the 0 mode, I get the eigenvalue. And then for the plus and minus, I get some coefficient that depends on the conventions. In the one that I showed in the notes, it's something like this, which is kind of odd if you have in mind the SU2 ones, but it's useful in the SL2R model. Okay, fine. And then you get the rest of the module. So the descendants to the state are of the form something like JA1 minus N1, JA2 minus N2, etc. acting on this side. Okay, that's all fine. But we showed that these states have a problem, is that these ones, the continuous ones, are tachyonic, and the discrete ones have a bound on the spin, which is so J is always a spin, and H is always going to be the space-time weight, so the weight of the holomorphic weight in the boundary theory, right? And we saw that for these states, for the natural states that come from the H3+, which are actually, if I go from this by analytic continuation to the AdS3 model, so the SL2R was the Wiener model. This H is the holomorphic weight in the boundary theory, so the CFT2 in the AdS3 CFT2 correspondence, and this is smaller than K over 2. So these two things are a problem because we cannot really have high, all the weights we would expect from the boundary theory, and we don't have anything coming from the continuous representation. And the answer to where are the rest of the states is that we need to include vector flow sets. So this was kind of the conclusion of the second lecture, and the idea is that So any questions about where we're going, or about the next the last lecture or something? Okay.
So for
Yes.
the hard states, alpha is the imaginary part of J.
No. So
It was J was 1/2 plus.
yeah. So for CJ, I have alpha. I have J is 1/2 times, I know. In the notes I usually use S, for example, but whatever. This some belongs to the reals. But M, the eigenvalue can take values which are alpha plus n, where n is an integer and alpha is some number, some fixed number between 0 and 1. So it's like the fractional part of the M. But the main point about this alpha is that it's not set by J. It's independent. Okay, so what were the spectrally flow states? We saw it at the classical level, but at the algebraic level, at the quantum level, what happens is that you can define, so you have your algebra, right? You have your affine SL2R, which is generated by the holomorphic currents, which I write like this. And then you have a set of automorphisms labeled by some integer omega, which is the spectral flow charge, let's say, which is just to say that if you define some tilde currents which look like this, so for plus minus you shift the indices, and for the 3 you just change the 0 mode. I probably have a fine, good. So if you define these new currents, these tilde currents satisfy the same algebra as the other, right? So I'm usually going to talk about these ones, so the ones without the tilde are the physical ones, because those are the ones that we're using to measure everything. But these satisfy the same algebra, right? So we have a set of states. And now I'm going to define the spectrally what I'm going to call the M basis. Yes. Just give me a second. Yes.
I can define M to be any real number. M minus M bar to be an integer without ever mentioning alpha, right?
Sorry, you can define what?
M to be some real number.
Yeah.
And M minus M bar is an integer without ever mentioning alpha.
Yeah.
I think one can do that, right?
Yeah.
Yes.
Yeah, the only so
if I do that, that's what.
So single valuedness of the wave function, that is not the difference between M and M bar has
Yeah.
an integer. But then the actual the sum can be everything, anything you want. It's just that you for a given representation you fix it once and for all, and that's it.
You do what you do, but you have two modules which have the same alpha. This way, then they would be the same.
Yeah.
Okay. Yeah, just please interrupt. This is kind of this is the important lecture for me, so whatever gets across, that's the important part, and then I get where I get. Okay, so I'm gonna define states, which are I'm gonna write like this, which are primaries. This is a primary state and a fine primary state with respect to the current J A tilde S, right? For a given value of omega. Let me add some little tweak here to say I set the omega here, right? Have an omega. And then for a given omega, I can define the tilde currents like this, where I have this omega here and this value of omega here. So I'm going to define this guy to be exactly a state with those properties there, but with respect to the tilde currents. Okay? This means that I can write exactly the same equation, saying that I have j tilde, I know, 3, j tilde a n larger than 0 on j m omega being 0, and j tilde 3, 0 on j m omega giving me m times j m omega, and j tilde plus minus 0 j m omega giving me some coefficient times j m plus minus 1 omega. Okay, but then you can undo this thing. You can write them in terms of the physical currents, and that tells you how these things act on this state. And you immediately see that, for example, if you look here at this guy, this tells you that the J plus only annihilates the state, this state, for n larger than omega, and not for n larger than 0, right? And the J minus annihilates the state for n larger than minus omega. These are the two first properties that we get. And this tells you that this flow state, Jm omega, is not an affine primary. Okay? It does satisfy some nice properties. For example, it's still true that if you take J lines here, that if you take J3, it's still an eigenstate, right? But now the eigenvalue, you have to add this piece here. I put this on the other side, right? So I get m plus k over 2 omega acting on J m omega. And you can also shift the values of this guy, give you something like J m plus minus 1 omega. But now here you have to put the guys with plus and minus omega, right? I here is 0, so I get plus omega or minus omega, right? So this is plus minus omega. Okay? So these are the kind of properties of this guy under the physical current. Normally, in any textbook Quasi-Minow model, you don't consider this state, because the road you follow is, okay, if I take affine primaries, this guarantees that the states are going to be Virasoro primary, right? Where here I'm using the fact that we use the Sugawara construction. But it's not, the converse is not true, right? So you could still have Virasoro prime, and this is, normally this is useful, this is enough, but here it's not, as we saw last time. We need to consider additional states, which are still going to be Virasoro primaries, but they are not affine primaries. So these states here. How do you see that they are still Virasoro primaries? So this is not true in the zero mode. And so you see that here there's no shift in the index, right? Because J plus and J minus don't appear here. They don't appear in the new ln tilde. And the reason for that is that usually you had, so in ln, the L's, you can basically think about them in terms of the J plus, J minus, J minus, J plus, etc. So the energy momentum tensor, in this case, something like this, right? They have to do all the normal ordering and so on, but kind of heuristically what happens is that every time I push an index here up in this way, I push the other one down, right? And so in the end, it doesn't do anything. What actually shifts something is the shift in this J3, and this ends up giving you a linear term from here and a quadratic term which is here. Okay? But here, there's no shift in the index. And from this, you can conclude that not only do I satisfy these properties here, but also, and more importantly, the Jm omega state is a Virasoro prime. In order to construct the worldsheet theory for things in AdS3, that's all I need. Right? I don't need anything else than that. So the two important quantum numbers, yeah.
Can you maybe you mentioned this in the previous lecture, but like, is there a necessary and sufficient condition for when I have to look at these Virasoro primers that are not African primaries? That you mentioned, like in the textbook was Witten, you usually don't think about those. And so is this now because I have some non-compact SL2R? Is this because of the special form of the spectral flow that makes it so that
it's kind of a mixture?
Is there an easy criteria to apply to think like, oh, those I have to consider?
So whenever it's Euclidean and compact, you never need them, right? But then how it enters in this game is kind of a mixture of the effects between being Lorentzian and non-compact. So what values of M you actually consider, and the fact that your target space is non-compact. But I didn't think about it too much, but I never read a kind of necessary criterion for Hall. I know that. So in this case, so whenever it has to do with the kind of the signs that you get here. For example, in SU2, you get kind of these signs. You can do the same, and you get kind of these signs kind of shifted, and you can still construct these guys, and you check, and these guys are still Virasoro primaries, but not affine primaries, and so on. And then you do the map, you do the algebra, and then you recognize that they are actually descendants of the old state that you already have. Kind of particular combination. But in this case, it's not true, and I'm going to show that in a second.
Okay, so you still have to show indeed that those Virasoro primers are not descendants of
exactly.
the affine primary.
You still have to show that these things are new.
Sorry, is the central charge preserved by the automorphism?
Yeah, everything is preserved. Yeah, central charge is still the same. It's still 3 equals 3k over k minus.
Is it possible to have a version of this discussion also, like I can forget about the Virasoro? Let's imagine I just know the big algebra, they're fine.
Yeah.
Then the question is basically, is every module decomposable into highest weight modules? And what you say is that it's not the case here.
I think in compact it looks
Exactly.
In compact, it looks
Yeah, so the non-compact nature of
exactly. So I think that's the answer to your question.
Yeah,
You can even forget about the Virasoro. Here it's just that there are modules which are not highest weight. So if you just look at the highest weight, obviously you're missing something. And then it happens that the non-highest weight, there are actually some of highest weights of the Virasoro.
Exactly.
and they're not descendants of the highest weights of the.
But it's not only non-compactness, because you could do the same in the pure H3 model, right? And you can show that what happens is that these states are there, but they're not necessary for consistency. So you can build your H3 plus model, which has the non-compact target space, and you can have a closed spectrum where everything kind of interacts with what it should, and there are no new states generated in the correlation functions and so on, and you have a consistent modular invariant partition function and a consistent 4-point function which factorizes in the known channels which are pointed in the spectrum. And all of that works, and you don't need to construct any of this. You could, but you don't need it. Right? You have a consistent model without them.
No, you need it, because if you don't do it, then you don't get a modular invariant partition function.
In H3 plus you do.
In H3 plus, how can you get that? If you just consider omega equals to 0 sector, then write the phrase the q to the power L0, q to the power L0 bar, I don't think that's modular invariant. It's just
we can discuss, but I'm pretty sure it can build it in modular. But okay, we can discuss that. So I think there's part of it which is just a representation theory, I agree, but there's some part of it which is where could you restrict or not, which also has to do with which values of M you're actually considering. So the M is the energy here, so on. So these kind of things for those things, it's kind of important that you're actually in the Lorentz set. Okay. So how do I show that? So the important quantum numbers here are two. One is the eigenvalue of J3 here, right? This guy. And the other one is, okay, this is actually a Virasoro primary, but this tells you that the weight changes, right? So the value of the conformal, of the worldsheet conformal dimension changes. And now the result is the old value, right? So this was what was already there. And I have new terms that come from that, and they look like this. Omega minus k omega. Okay. And this you already see where it is. What's going to happen, what I'm going to show in with the weight diagrams, is that, so for SU2, for example, you get here a plus and here a plus, right? And so so in that sense, anything you just add, you just increase the weight by increasing the value of m, for example, the value of omega and so on. And so you are increasing the weight, which is exactly the same you do if you increase the sentence, right? But here you are decreasing it. So you get lower values of the conformal dimension than anything that was there in the original representation. So they can't be part of it. Yeah. Okay. And there's one more kind of important thing, which is the following. There's two more important properties. Well, one more important property is that also, even if you have this thing here, I just showed you there that J minus annihilates the state already starting from large for modes larger than minus omega, right? So in particular, it's still true that if I do this, I get 0. Just because 0 is larger than minus omega. Okay? And this tells you that in terms of the 0 mode representation, in terms of the 0 mode algebra, so the thing generated by this guy, this is the lowest weight representation. Right? So for the 0 modes in SL2R, we know that we have the continuous and the discrete representations, right? So the guys that I have here at the beginning, but without the hats. So the 0 mode representation, not the modules, not the affine modules. But this tells that this guy is the lowest, is the kind of bottom component of lowest weight representation. I'm gonna make that clear in a second. But the point is that, again, I have some guy, which is J, I start from this, right? And then I can act with this guy. And it's going to give me something which is not particularly easy to write in terms of the usual states, right? Because I'm acting with a mode, which in terms of the tilde currents is kind of strange, right? But this is my actual physical guy, right? This is the guy that, for example, that I want to identify with the translation generator on the boundary, right? And this is going to act non-trivially. It acts non-trivially because, again, 0 is smaller than omega. So I'm below the values where J plus annihilates the most, where J plus annihilates the state. So it's going to give me something, and I can keep acting and acting and acting, right? So this means that this is, I can just define it in this way. So in terms of the original guy, this is just some descent. It doesn't change much, right? It's just I can just keep going and going and going. So what I have is a zero mode representation where this guy is the lowest weight state, right? Because I am at the bottom of what I have. When I act one more time with J0 minus, I get 0. Then I can keep increasing the eigenvalue by acting with J0 plus, right? And this is exactly what we call, what we would call some kind of D plus with respect to the J tilde currents, right? But it's not. It's just about what happens with the zero modes, right? Not the full affine algebra, because it's not a primary or anything like that. It's just a representation of the zero modes. So now I can act. This is the lowest weight representation, and then, and in order to kind of characterize it, I need to give one more property, which is to say what's the spin of that representation, right? And the spin of that representation, since this is the lowest component guy, the spin of that representation is exactly the eigenvalue of J03, because it's already the lowest one. So the lowest one is the one that has projection equals to the spin. And so the end result is that the spin, which is what is going to correspond now to the actual weight in the space, in the boundary theory, in the space-time theory, is the old m plus k over 2 omega. And this is the way in which you avoid the unphysical bound, right? Because this is going to be the weight, this is identified with the weight, again, of the holographic CFT. So now it's not bounded anymore by k over 2, right? You can have, for example, for the chiral primary states in the supersymmetric theory, this m has to be, there's a constraint from the Virasoro condition that is that this m has to be, that this has to be the original lowest weight. So this has to be not m, not any m, but exactly the little j. The little j had to be between 0 and k over 2, but here now you can add units of k over 2. So you can go beyond that bound. Nothing stops you. And this is where the additional state that we need lives. But okay, this is a bunch of words and representation theory, so let me kind of try to. Yeah.
What happened to the tachyonic continuous representations?
Those are not in the spectrum. But no, but what does happen is that what I said here, that this guy is the lowest weight, is the bottom component in the lowest weight representation, is true no matter where I came from. This condition here is just about the spectral flow automorphism, right? So this is true whether I came from a continuous representation or whether I came from a discrete representation, right? So now I'm gonna get two representations, which I'm gonna call Cj alpha omega and Cj plus minus omega, right? And now these can actually be in the spectrum. And this is the same that we saw at the classical level, where for the space-like geodesics, we couldn't solve the Virasoro condition. These were tachyonic. But when we flowed those, we got actual physical states. Here is the same. You have physical states coming from here and coming from here. But in terms of the zero mode representation, you always land on lowest weight representation or highest weight if omega is negative. Right? If I change the sign of omega, I invert the roles of plus and minus, and so it becomes the highest weight instead of the lowest weight. Let me add the condition. Okay. Again. Yeah.
Yeah, I have a question. So in this spectrum that we found, does this mean can I tune my parameters like m, k, and omega such that I have states with arbitrarily low conformal dimension?
with arbitrarily low.
Yeah, like basically there's no gap in the spectrum.
No, M is bounded from M is J plus N.
Yeah, so
So J can be 0.
J goes to a half, not to 0.
Okay, J goes to a half.
Yeah.
Okay.
So
the smallest stage is a half.
if I start from D plus, for example, and I do spectral flow, I have M, which is J plus some natural number, right? J is between a half and K over 2. Well, we are going to see today that actually this is K minus 1. There's a quantum correction here. There's a bound. And to look at the spectrum, you should kind of only consider, you don't need to consider more than positive omega, because it's kind of what happened before between the D plus and the D minus. You can think of the guys with positive omega as the incoming states and the negative omega as outgoing states. So you don't need to count them twice. So if you look at, I'm going to write the spectrum at the end. But if you just look at, if you want to know the physical spectrum, you can stay in this area here, and then you also do it with the continuous presentation.
And so does this mean that then above the vacuum, so the vacuum with h bar equals to 0, then the first state has h equals 1/2 and h bar equal to 0? Can I have a state with persistent?
H bar is the same as this. I have to do this on both sides, not only on the.
But J is not h minus h bar. J is not.
No, J is, so in the unflowed spectrum, in the unflowed sector, J is H. Then I have H bar, which would be J bar, which in this model has to be the same as J. So I'm in the unflowed spectrum. I was looking at the space-time scalar.
Okay. But then I can have, if it's a scale, so in the scalar sector, then the first state above the vacuum is h equals h bar equals 1/2.
Yeah.
Okay. And instead, in a spinning sector, can I make this lower, or is it still?
No, you can always go higher than this.
So it will always be higher than that.
Yeah, I can only add units of K over 2.
No, but without adding them, I want to like keep it as low as possible.
No, that's the lowest.
So the lowest I can have for in a spinning sector is still like 1/2 0, basically.
Yeah.
Okay.
But 1/2. Yeah.
No, 1/2 is in the scalar sector.
Yeah, but okay. So depending on the usual, like in SU2, the usual way of building in the unflowed sector, in SU2, what you do to build a modular invariant partition function, one way is to use the diagonal representation, where you always set J equals to J bar.
Yeah.
Right?
Okay.
That's the kind of state I'm looking at here.
Okay, so you're in the diagonal. Okay. But does that have to do? So that does not imply that the holographic CFT is diagonal.
No, because what happens, you see it here, right? Because then I have to do the same spectral flow on both sides, right? But I could have in the float sector the different M bar, right? M and M bar they don't have to be the same. The only constraint that you have is that M minus M bar has to be integral. Okay, but these two don't need to be the same. So this way you can construct operators which are not scalar.
Okay.
You need to have the same omega, and they need to come from the same representation, but still you can choose different values of M and M bar, so that gives you different values of H and H bar.
And so I will always have a finite gap in the spectrum for every spin.
Yeah.
Okay. It's nice because, for example, if you set like a CFT with Virasoro times U1 symmetry, you can prove that the twist gap vanishes for any CFT.
Why do you need to do the same? Why do we have omega the same?
And this is then that remember in the first lecture that it's because of the boundary conditions of sigma going to sigma plus 2 pi in the worldsheet, right? So if you do different left and right spectral flow, you change the y, which is the circular coordinate in space-time, which was something, but it had some y0 before spectral flow, whatever that was, and now it gets something like sigma plus omega left plus omega right over 2 plus tau omega left minus omega right over 2, right? So this, you have to kill this, and you get a similar factor for the t, you get a similar factor changing the sigma and the tau. And so you get kind of closed timeline curve if you don't kill this term. So if this is not the same as this, and this has to be, and then this tells you that this has to be the same integral on both sides in order to have the correct boundary condition.
I think what Mariana is saying is that it's true that you will have to, if you want explicitly in SL2R, but since you lifted it to the universal cover, T is no longer compact. You have to kill that term, right?
Yeah, exactly. So if you work in SL2R,
you do have omega left and omega right.
yeah, not in the universal cover, so the actual SL2R where time is compact, you can have different spectral flows on left and right. Or in SU2, you can have different spectral flows on left and right. Okay, let me try to draw a couple of pictures. Do it. Yeah. Okay. So what's the usual weight diagram? So for an unflowed representation, so Bj plus minus, right? What do I have? I can draw a weight diagram, which of course I'm gonna get wrong. So let's say something like this. So I'm drawing the eigenvalues of J03 and L0. So what do you have? You start with the line, which is that this is the JJ guy, let's say. It has eigenvalue J, and the eigenvalue with L0 is minus J minus 1 over K minus 2. Right? So I have a point here. And from this point I can build the whole representation. Right? So what do I do? First of all, I can act with J0 plus. Right? That increases the charge without changing the value of L0, the eigenvalue of L0. So I have another point here, another point here, another here, etc., etc. And this goes on. Okay? These are all the states, these are the operators or the states that correspond to the Jm. Right? These are the primary. Then I can, from each of these, I can act with J0 minus 1, J plus minus 1, J minus 1, and J3 minus 1. That gives me one guy that goes here, one guy that goes here, and one guy that goes here, because they have charge plus, minus 1, and 0. Okay, so I get 3 points here. But to this is not unique. I can also get to this from here, right, and so on. So this here is J minus 1. Okay, and I can continue like this. I have a state on top of this. And then I can keep doing this, blah blah blah, etc., etc., etc. Okay, that's the weight diagram. And you see that the eigenvalue of L0 is always bounded by bounded below, but it cannot go beyond the primary value. And also because I have a range of validity for my J, it's overall bounded below, right? There's a minimal value for this thing, right? And that's also true for the continuous representations, because in this case I have J equals 1/2 plus I something, and this ends up being this guy here, J minus J plus minus J minus 1 ends up being 1/4 plus S squared, where S is the imaginary part. Okay, so what happens when I do spectrum? Yeah, this is for the plus. If I have the minus, I have to reflect here, and if I have a continuous one, this just continues here. Okay, and then so it's just an infinite line here, and then everything above. What happens now with spectral flow? I try to use some color. So let me do now the guy that corresponds to the affine representation for the same j, the plus and omega equals 1. Okay? So let me take one more color. Let me say that I take this guy to be the first one. Okay? So where does it go? I know that the eigenvalue shifts from j to j plus k over 2. Right? And I know that the weight goes a bit down, right? And now it's minus j minus 1 over k minus 2 minus, I will have to put m times omega, but omega is 1 and m is j, right? It's the first one. So I get minus j. And then I get minus k over 4 times omega squared, but omega is 1. Okay, so I start with the point, this point goes here. But now I look at the next one. And the next one here, I change m by 1 unit, right? And if I change m by 1 unit from the formula of the weight, which is something like this again, so the one before spectral flow minus m omega minus k over 4 omega squared. I change m by 1 unit. That means that I go a bit below, in this case 1 unit also in the weight, in the eigenvalue of L0. This is L0 and this is L0. So the next one goes somewhere here. Okay, I change 1 unit here and 1 unit here. And then the next one in this line goes 1 unit below here. And then the next one here, and then the next one here, and so on. Okay? So who does the job of going from here to here? It used to be J0 plus, which now I can write as J0 plus tilde. Right? Because it's the guy that acts exactly as before. But now J0 plus tilde is not the physical J0 anymore. Now it's J plus 1. And that's why it's changing my, because this doesn't commute with L0. Right? That's why it's changing the weight. But now for each of these, I can still act with J0 plus. Right? So for each of these states, I can have all of the things that come here. I can have all of the things that come here. I can have everything here, etc. Okay? But now, if I continue this way, this is where it stops. Because first of all, in this direction, I said that J0 minus kills it, right? So this ends here. And that's true for any of them, right? There's nothing to the left of each of these points. But what is true is that I can go to the next guy that was here, right? The guy that was there, now I have to act with J tilde minus 1, which was this guy here, right? But now that guy is J minus 2, right? So I don't go 1 unit above, I go 2 guys above, right? And each of them just goes something like this. So I have like an angle here between this line and this line. And then I still have, I can act with anything and I still act something. I have all of the states here. And of course, I've already managed to fuck up my color coding. That's okay. I have anything else here. Right? So this is what spectral flow does. It takes your weight diagram here and it kind of tilts it in this way. Because now, again, what was J0 plus, which is now J tilde plus 0, doesn't commute with L0 anymore. Right? So this is what it does.
Wait, what's the first red line above the blue line, like the one that doesn't have a white point? Like doing it.
So you do the same as before. Now you act with the physical J3 minus 1.
Okay.
Which
White point and
Yeah, with the J. Okay, yeah.
So it's not.
I was thinking about it in terms of the tildes. How do you get there?
So this guy here, if I'm not mistaken, is this guy here, right? The eigenvalue is not the same because I shifted J03, but I don't shift the mode. The only reason, so I'm highlighting these two lines because these are the two boundaries there. This guy is not on one of those boundaries. Okay, and you see here already that whatever I do, if I have positive vector flow, the eigenvalue of L0 is unbounded below, right? So that automatically guarantees that these are new states. You can do the same exercise in SU2, you draw the weight diagram and so on, and in SU2 you just see that it just reshuffles that. There's nothing new. But here there is something new. Anything I do with a positive omega is new. And I can do the same with here I did the plot with D plus, but I can do the same with the D minus and the same with the continuous guy, right? So for the continuous, for example, I would have just an infinite line here, right? And everything on the right of that. Picture.
D minus with omega equal +1.
Yeah, that's what I'm doing. There's an interesting point. Which is, this kind of game is still true if I do the, for example, D minus with omega equals -2, for example, or -1, something. Or if I do D plus for omega equals -2, right? Instead of tilting it this way, I tilt it the other way. And I'm going to get something that looks like something, the boundaries look like this, right? But there's one for which that's not true, which is the guy. So, except that if you take the original D plus and you do only -1 unit of spectral flow, you tilt it exactly the right way to get the D minus, to get one D minus, not the corresponding D minus. There's also a shift where you go to J to K over 2 minus J, but it's one of the old guys. And you can see it very easily because if I take the guy which has J, not do this wrong. I take the guy which has J minus J omega equals 0, right? You compare it with the guy that has K over 2 minus J, K over 2 minus J, and omega equals 1, minus 1, right? You check for, you ask me, for example, what are the values of H here? So the value of H here is just J, right? Sorry, the eigenvalue of J03. The eigenvalue of J03 is just minus J, okay, because it's the second guy here, and I have no spectral flow. And here, the eigenvalue is K over 2 minus J, so M plus K over 2 omega, which is K over 2 minus J plus K over 2. Right. The eigenvalues are the same. And you can...
Yeah, minus K over 2.
Sorry, minus K. Yes. Yeah, this plus, but I have one. And then you can also check that if you do the delta here, this is just the usual guy, right? But now if you do the delta with that formula, with the formula that was here, I already erased, Let me say what you get. So here you get minus j, which is minus k over 2 minus j minus 1, which is k over 2 minus j minus 1, divided by k minus 2. Then you get minus m omega, which is plus k over 2 minus j. Then you get minus k over 4, and then omega squared, which is k1. If you just do the algebra, you get again this. Okay? So these two guys, and these are the guys from which I built the full representation, right? So these two representations are the same. What happens if I take the representation, which is this one, so the guy with d with k over 2 minus j plus and omega equals minus 1. So you start from something that looks like this, where this is k over 2 minus j, right? And you rotate it in exactly the correct way in order to get to something which is so this is this guy, right? And then if you rotate it with vector rho minus 1, what you get is exactly what you would have called the representation of j and no spectral field, right? You just rotate it in the other way and you get exactly something that looks like this. Okay, and everything that's inside. So this is actually not a new set of states. This has a name, well, has several names related to what's called FDD duality, for example, and so on. But at the algebraic level, it's just the SL2R series identifications. And it's a bit more general than only omega equals minus 1. I can always relate a d plus with some omega and a d minus with one more unit of omega, right? So all the states which are d plus omega of k over 2 minus j is always the same representation as the d minus j omega. So all of these guys are always the same. Okay? For the rest, everything is new. Because if I keep rotating more, I again get unbounded values for L0. And here you see that one important thing is that if you start from, if you want to see it in this way, right? You remember that you had a bound on J. The bound on J was that was something like this, right? But you see that if you go from, if you want to interpret it in this way, you should put the same bound on k over 2 minus j, right? And so what it does, and this is the origin of having the minus 1 here. Because if j is larger than 1/2, then Caillou asking that this guy is also larger than 1/2 is something that was there. So this is the actual physical bound on the what's usually called the unclosed spin. And so in the end, you can ask, what's the final spectrum of the theory? For the SL2R Western model, you can write it for the full Hilbert space. You can write it as the Hilbert space in the unclosed sector plus the sum of the Hilbert spaces in the closed sector, right? This guy, we know what it is. It's just the, let's say, the integral from j going from 1/2 to k minus 1 over 2, with this bound there, of all the representations which look like this, because I'm using the diagonal construction, as I was saying, right? And again, I don't need to count both the D plus and the D minus because the D plus are the outgoing states and the D minus are the ingoing states. So they just conjugate to each other. So I just need to count this. That's it. It's the spectrum in the unflowed sector. And there is no continuous state here because they were tachyonic, right? And then for this guy, I have more stuff. This has the integral again in J in 1/2 and K minus 1 over 2 of the D plus omega. Let me add the hats here. Plus the integral of J being 1/2 plus IR of and the integral in alpha between 0 and 1 because that's all the allowed rate I have without overcounting of this guy. Right? So the closed sector, I have both the discrete states, i.e. the short string. These are the long strings. And these are the quote unquote in terms of the geodesics that we were looking at in the first lecture. Okay.
This spectrum by itself gives you, if you sum over it, it gives you a modular invariant partition function.
Yes.
Which is the
Exactly.
And are there other choices that are non-diagonal, which still give modular invariant partition functions?
It's a good question. I don't know if anybody tried. Presumably, thinking about the SC2 states, I would say yes. SC2 case, I would say yes. But I really don't know. Do you know if anybody tried?
Namathinagudi's approach was from the path integral point of view.
Yeah.
And they showed that the path integral reduces to the trace of these guys.
Exactly.
So yeah, so in other, if you take the non-diagonal one, I don't know what exactly you are calculating.
Yeah, it would be another theory.
Whether it's consistent or not.
Yeah. I mean, if it's, yeah, you could check if there's anything that is consistent with modular invariant.
Honest answer is I don't know. I don't know if it can be done or not. I never saw any paper where people try. I didn't try.
These K-equal there are choices.
There are choices. I guess. Okay. I don't know, what do they correspond to, these choices?
Oh, that's yeah, that's
okay, yes.
Yeah, it's probably that might be related to what you were saying. Yeah, you were telling us about the other day. Yeah, right.
Or they're changing the state of the boundaries.
But that's more like seeing things not from the vacuum, but from the state where you have some defect or something like that. It's not the, let's say, vacuum partition function. Yeah.
Just to have an idea of this, like a visual thing, if you plot it on the plot you made before, there is kind of an excluded
Exactly. Yeah,
parabola.
something like this. Yeah.
So you can feel literally every point except for this excluded parabola.
It's going to be inverted parabola. Exactly. Okay. Any questions before I move on? This is the finally the full spectrum.
Can you remind us what was the intuition behind why is the continuous representation the long strings and the discrete one the short strings?
You can.
Your interpretation in terms of geodesic and AdS3.
It's just because if you can escape, one way to say it is that if you can escape from the kind of, you can see the interior of AdS as some kind of potential barrier, and if you something like this, and if you are above that, you have a continuous spectrum of energies, and if you are inside, you have a discrete spectrum of energies.
Okay, and this corresponds to really the string going all the way to the
Exactly.
boundary, or staying in the. Okay, yeah, great.
Okay, So now let's move on to correlator. What time is it anyway? Okay, let's do 10 minutes and then we do break. Okay. Okay. So again, correlator. The first part, which I'm gonna spend only this 5 minutes before the break on, is the unflowed section. And you can basically argue that the only thing you need to do is to take the correlators in H3 plus. By unity continuation, I mean unity continuation in J or M. Okay? So what do we know about this? Well, thanks to the papers by Teschner in the 90s, something by Kovensky as well, and then Milan and collaborators, we basically know everything we would want to know. The usual thing you know from you want to know from for a CFT. So you can solve exactly, and in particular, you can check that. So if I have my states which are like this, right? I can associate to this state some vertex operators which are like this, right? And I can ask what the correlators of these guys are. So J1, M1, Z1, Z1, etc. Right? So let's say V2, V3. Okay, I can ask what these guys are. First of all, I have conformally, I'm looking at 3-point functions for now, for completeness. First of all, I have conformal invariance in Z, right? So I know what the dependence in Z is. Then I have a bunch of world identities which are related to the SL2R currents, not the Virasoro part, which tell me, for example, that because I have this guy here, which changes the charge from M to M plus 1, right? I can change, I have some recursion relation which looks like this, which the guy where I'm doing this very schematically, but the guy where I take M1 to M1 plus 1 with some coefficient, that would be some other coefficient, the guy where I take M2 to M2 plus 1, and the correlator where I take M3 to M3 plus 1. Right? This is just the world identity associated to this global mode of the affine algebra. Okay? But we know, so in principle, this looks kind of ugly to solve. In the SU2 model, we know what the solution to these things is. These things, this J and M, are the spin and the projection of the spin, or the isospin and projection of the S spin. And we know that the solution to these recursion relations is given by the Krebs-Gordon coefficient. Right? This is what these things are. So the solution to those recursion relations, and you have one for J0, and then you have one for also for J0 minus, and one for J03. So this one is just charge conservation, for example, and this one is another relation which is a bit more complicated. And you get the analogous thing to the Krebs-Gordon coefficient, but for SL2 instead of for SU2. Okay, these are more horrible because life is more complicated, and because you want these things to be actually analytic in the spins and in the projections. And for those to be analytic, you have to change a bunch of factorials for a bunch of gamma functions and so on, hypergeometric functions, etc., etc. But we know how to solve it much more simply than that. We know that for each of these guys, you can also use the X-basis representation, right? So that you can build a guy like this, which is basically the sum over the allowed values of M of X to the M minus J Bj M of X, this X set. And we know that this X is not only a label, it's also the coordinate on the boundary field. right? It's a holomorphic coordinate on the boundary. And so the trivial solution to this thing is that in terms of the variable x, which is the conjugate to m, you also have conformal invariance, right? Because on this guy, the J0 plus acts as dx. So let me write it like this. You have an OPE between the currents, which is something like this. One over that. Some differential operator in terms of x, dj, x, z, where this guy is plus this operator, this 3, this operator, and the minus this operator. Okay, and you know that this is, again, these world identities are the world identities of conformal invariance on the boundary field. And so the final solution for this thing is that if you have some dj1, f1, f1, until dj3, f3, f3, all of these complicated identities can be solved by going into these spaces and just saying that I have some structure constant that depends on J2, J1, J2, J3, and then I have the usual, so Z1, 2 to the J3, to J1 plus J2 minus J3, etc. And then you have X1, 2 to the delta 1 plus delta 2 minus delta 3. And this is J1 plus J2 plus minus J3. Good. Right? So this is all the dependence on the Z, and this is all the dependence on the X's, which encodes all the dependence on the eigenvalues M through this transformation here. Okay? So far so good?
Now can you, so now you have the 3-point function for the operators defined in X and Z. From this, can you extract the correlation function? Can you invert this and extract the one only in Z?
Yeah, of course, it's an integral transform. It's just inverting this thing here. It's a Mellin type integral. You get a bunch of gamma functions and hypergeometrics and blah, blah, blah. And you can
That's not actually a sum, that's an integral. Not sum over M.
No, this is a sum over M because for a given J, the values of, for a given J and a given alpha, if you're in the continuous phase, allowed values for M are discrete.
Okay.
But you can invert it kind of at the same time for the discrete and the continuous by you doing some integral over the full complex plane in X.
Then does this mean that, so we can derive this from two different ways, either from the worldsheet world identities or from consistent with conformal symmetry of the graphing?
It's the same, right? The world identities in this language are the same as the world identities for conformal symmetry in X.
Yeah, because it's the same as a 2R.
Yeah.
This is very strong, like that, right? Like you're fixing the optic coefficients of the full spectrum,
No,
not the flowless sector.
But not all. I still have to tell you what this thing is, right? I still have some.
It wasn't the point that you can find the CJs.
Yeah. So first of all, by this nice trick, I can find all the dependence on the M's. Now the question is, what's this thing in terms of the J?
Okay, so
There's still a structure constant here that only depends on the spin. And the answer for this was found by Teschner originally, which is that this guy. Do you remember that I told you that you could, in the H3 model, you could kind of had a fields which were for example beta, gamma, and phi, right? So this is some non-compact scalar, and this is a beta gamma system in the free field approximation, right? So near the boundary. You can integrate these two out, and then you get kind of a Liouville theory. You get an effective potential for phi. You get some kind of a Liouville theory for phi. So what Teschner did is he took the well-known result by Samolotchikov and Samolotchikov, which computed the 3-point function of Liouville theory exactly, the analytic expression in terms of the of the conformal dimensions, and he derived from that. So just from pure, the only two things that you use in that computation is the Nicolas homological equation for the 4-point functions and the crossing symmetry equations, so just consistency of the CFT, and you derive exactly what this thing is, right? It's a bit what Sylvain was telling about in the journal club last week. So you can derive this exactly from the CFT formula. This Dorn, Otto's, homological, and homological, which kind of did at the same time, and they gave an explicit closed expression for this guy.
So they are exactly equal to the DOCC formula, or you derive them?
Yeah, you have a map between the Liouville momenta and the spins J, and it's exactly the same formula.
How can this be exact if you've obtained it by first going to this pre-approximation and integrating out the B gamma, the beta gamma?
You can show it. You can show that you don't need to go to the free field approximation. You don't need to go this way.
Okay.
You can show that the Nicolas homological equation in the H3 model becomes the different ways of writing it become the null state equations in the Liouville theory, and then you derive this exactly. So this is no.
Does this mean that now we have two CFTs which have different spectrum but same OP coefficient, which are Liouville CFT and H3 model?
Yeah, it's not that, again, you have a map between the spins and the
Yeah,
momenta.
the spectrum is different. So yeah.
But if you just look at, that's what I was saying. If you just look at the H3 model, you can just focus on the purely continuous state. You don't need to go to real values of J, because that comes from the analytic continuation to the AdS3 setting. Right? You just stay in the Euclidean non-compact H3 model. Your whole spectrum is built from and you don't impose the Virasoro condition, which is the physical condition for things in AdS3. You have modes which are you can build a consistent spectrum only from the continuous states. And those continuous states are just analogous to the Liouville states, to the Liouville vertex operator. Spectrum is analogous to that, and the 3-point functions for that theory are exactly analogous to the 3-point functions in the Liouville theory.
Does this mean that then the Euclidean H3 model is just Liouville in disguise? I mean, if two CFTs have the same data, they're the same CFT. Right?
It has more symmetry. It has an affine symmetry which the Liouville theory doesn't have.
How do you see that if the spectrum is the same? Like you will, all the local operators that you can build will be the same. Maybe it's Liouville that has this secret symmetry.
All of this is nicely discussed by Sylvain in the lecture notes on CFT on the plane. And basically the argument is that Liouville is the simplest possible non-compact CFT with just Virasoro symmetry, and H3 plus is the simplest possible non-compact CFT with non-Abelian affine symmetry. What can I say?
So
the difference is that the spectrum is not exact. So the spectrum in the values of J is the same, but you have more in H3 plus because you have the labels which are these X's. Okay. The spectrum in terms of J is the same, but then for each J you have a complex label which is X.
And that's where this extra symmetry acts.
Exactly. Okay. Yeah. But since I've encoded all the dependence in X here, then this part is analogous to the.
Can I just do this for like turn this around and take Liouville CFT, take whatever symmetry group G that I want to, and apply this recipe and get a new CFT which has just the same or like the same spectrum and OP coefficients as Liouville plus a new symmetry. Can I just construct arbitrary non-compact CFTs with any symmetry using this recipe? Like I introduced some new X variables and I introduce some generators that act on the X's. Then I will have a new label on the spectrum, M. But do this instead of for just SL2R for any group G.
The honest answer is I don't know. Maybe there are some constructions of that type, but I never really tried. Okay. And the last point I want to make is that from knowing this thing exactly, which again is given to us by the original computation. This is a beautiful computation, but I just don't have really don't have time to go into it. From the 3-point functions, you can derive both the 2-point function and the OBE coefficient. And this is the formula I'm kind of interested in, which is that you can show that in the unclosed sector, if you have some J1, X1, Z1, and the J2, X2, Z2, you have an OBE which looks like this. This is the sum of these guys. And then you have an integral over x, and again and these coefficients here, J1, J2, J3, and these guys here. There's a kind of a reflection going on, but that's not very, the technical point is not very important. This is from the reflection. There's a reflection here in between going from J to 1 minus J in the spectrum. That's what this thing comes from, but it doesn't change much from what I'm saying. But the main point is that, so here, because X and J are really the labels of the representation, when I do the OBE, I need to sum over all of them. These are continuous variables. So I have an integral over J and an integral over the full complex plane in X. And the important thing is that while this is true for the H3 plus model, if I want to do the same, if I want to do the analytic continuation, I'm going to the AdS3 model. So this sentence that I wrote there up top, this is actually a complicated thing to do, because this guy, we know it exactly, and it has poles all over the place, right? All over the complex plane in the spin spine in J3, right? So if I want to take, for example, J1 and move it from and move it from the values of the H3 model, which are a half plus IR, move it, for example, to real values, right? Which is what I need to do to go to the AdS3 case. Then what happens is that I have my integration in the J3 plane, right? So something like this. So this is the contour of my integration. There are a bunch of poles here on both sides. And when I start moving around the values of J1 and J2 to change the actual states I'm looking at, a bunch of these poles start crossing the contour of integration. So I need to pick up all of these contributions. And doing that in detail is complicated. And for the 4-point function, this was kind of studied by Mallasena and Noguri in the third paper. This is a very long computation. It's really non-trivial. But again, this is kind of old stuff, and I don't want to say much more about that. So maybe I ask if there are questions, and we pause for 10 minutes. So now I want to look at the exploration functions in the Mercalli flow sector, right? So this is really, I'm going to say now, is really this is where I start the new stuff. So I jump from 2001 to 2019. So this is Eberhard, Gopakumar, Gabriel, and Gopakumar, which kind of restarted this where it was blocked in 2019, and then several works that followed from there by them and also other people. So I want to look at correlators. I want to know how to compute correlators of this thing. Right, so I'm gonna use this notation. I'm gonna use these these operators. Look at correlators. So 3-point function in particular, 1 to n in general, of operators which have some ji, right? Then I was using the states which are j, m, and omega, right? This label, so I need to label the spin. The spin I was calling it h, which was kind of another way of encompassing what m is. So here in the x base, I'm going to use the label h. Then I have some omega I, and this is going to depend on x I and z I. The question is, how do I compute this thing? Okay. First of all, it is quite non-trivial for several reasons. The kind of zeroth order one is that it depends on many things, right? I have 4 quantum numbers plus the worldsheet coordinate. That's already kind of non-trivial. Also, I need to do, these things are continuous variables that can be can be complex, so I need to do it as an analytic formula in J and H. The only thing that's actually quantized, and in X also, but in X is going to be kind of simple. The only thing that's actually quantized is this omega here, and the difference between, I'm not writing it here, but I have an X bar and I have an H bar. The H bar can be different, I'm just not writing it. The only thing quantized is omega and H minus H bar, which is M minus M bar.
Why there is omega I? Thought you were in spectral flow to the whole spectrum, the same omega.
No. What I did, so the spectrum is the sum over all possible values of spectral flow I want. So I can have states with spectral flow 1, 2, 3, whatever I want.
And there is some redundancy.
So the redundancy is that here I can just get rid of it by only dealing with the with continuous and the pluses, so not including the d minuses, and also restricting to positive values of omega. So the x base is kind of irrelevant to look at the negative values, because if you look at this, if you try to, I'm going to define this now, but basically if you're in discrete sectors, for example, the residues of this guy at x equals 0, so the first order, second order, etc., are the states in the d plus, and the residues again around x equals infinity are the guys on the d minus. So it's all encoded here, so you don't need to worry about having putting omega negative. Okay. Now this is highly non-trivial, and the question is, what are the properties of this guy? So I remember that the state satisfies something like, first of all, that n. So for the guys between 1, the j plus, between 1 and omega acting on this guy, this is not 0, because this guy is not an affine primer. Okay? So how do I define this guy? Well, first of all, I want to define this guy by doing exactly what I did before. So what happened before? So in the unflowed setting, this guy is what I would have called the state associated to an operator. It was Vj, well, in this case Vjj, but this one was Vj j plus 2 of that. Okay. And this guy x, guy Vj in x, what it does is it kind of resums all of this line, contains the information about all of that line. Now I want to do the same, and it's still true that anywhere for any state, it should be true that this guy acts as a derivative in x, no matter if I'm talking about spectrally flowed states or not. This is just my definition of what moving in the x direction is. So now what happens is that for each of these guys, so this one, when I spectrally flow it, I land on this first guy here. The second one lands here and the next one here. But each of these is a different operator in the X if I want to do it in the X space. Because the J0 plus, if I want to resum the action of a horizontal line, it's still true that this whole line is what I want to call the J. So this would be the J, the value of H, which is the first one. So here I have JJ. So the M, the J that I get here is J plus K over 2 omega, right? The omega I chose, but in this case, the omega equals 1, but I can do it for anyone. And then summing over this whole line of guys is what I call X Z. Okay, so X is the guy that resums the action of the translation operator. So I move from the origin in X to a random point in X by doing linear combinations of this guy. Okay? But then I have one for each, right? I have another one, which is this guy. No, this guy here. This is a different X basis operator. This X basis operator is the one that has J, H equals J plus 2 plus K over 2 omega, omega, and X Z. Okay? And these guys are different guys. There are different states. They're really not in the same representation, and their properties here are going to be different because I'm changing the value of one of the quantum numbers, which is H. Okay, which is actually a very important quantum number if you think about it in holographic terms, which is because it's the weight in the boundary theory. Okay. So, but all of these states here, this one, this line, this line, this line, whatever, if I have for a fixed value of omega, they all satisfy one important property, which is that they are not annihilated by any of these positive modes. Okay? So what do the OPEs for these guys with the current look like? Well, we know that the simple pole of one of the OPEs with the current corresponds to the action of the zero mode. Here, what happens is that I have more non-trivial poles. I have higher order poles. So if I look, for example, at the OPE with J plus of Z prime with J H omega X Z, I get four things. I get three types of things. First of all, I'm going to get here the usual guy, right? So I have the mode here, the action of the zero mode. Then I have a bunch of terms, and then I have the action of the highest possible mode, which is non-trivial, is J omega, right? I have J plus omega, B J H omega of X Z. I'm not going to do the whole thing in detail. I'm just going to try to show you why this is a very, very non-trivial question. This is the simple pole. This is the highest possible non-trivial pole that I have, which is omega plus 1. And then I have a whole bunch of terms from 1 to omega minus 1 in the action of the other modes. And omega. Everything is in the node, so there's no. Okay, so these terms here, all of these guys are new. These were not there for the unflowed states. For the unflowed states, I just had a simple pole. And then, of course, I have the regular terms. And now the main point is, this guy, I know how it acts, right? I just said it has to act as the derivative with respect to x. It's always what it does. right? So this is the generator of the translations in the boundaries here. So that I know what it is. This guy, I also know what it does. I know it because the j plus omega, if you remember the formula, is the j tilde 0, right? So I know what it does is that it takes this thing has to be proportional to another operator appearing in the OPE between the current and this one, which has the same value of the spin, of the unfloat spin, the same value of omega, but m is shifted in 1 unit, right? Because this is the guy that shifts this m here in 1 unit. So all it does is it shifts the original h plus 1. If you remember, this h was m plus over 2 omega, so I shift this guy by 1. That's what this mode does. So it gives me something like this. Okay, okay, so far so good. Yeah. And this whole thing in the middle, I have no idea. It does something. It's just some. These are just some descendant operators in terms of this j tilde. They have no simple expression in terms of beta zero prime, right? And this is the big problem of how to compute these correlators. Is that if I try to use the usual kind of contour integration techniques in CFT, and I try to play with the contours around and so on, I always end up having to deal with these contributions. And these contributions, I have no simple expression in terms of something acting on a primary correlator. I really don't have, I mean, formally I know what this thing is, but then using it to actually compute what these correlators are, it's kind of complicated. I don't know how to deal with this.
You restrict to omega equals 1, you say it's relatively easy.
Yes, and that's kind of what Malefeno and Oguri had already done. They looked at the first non-trivial guy, which is easy because there's nothing you don't know. It's still a long computation, but you can do it with kind of, let's say, usual techniques in CFT. But this one is complicated. For omega larger than 2 or larger, I don't know what these guys are. I need to find a way to avoid dealing with this guy. And then, okay, I have some other OPs with the current, for example, with J3 and with J minus, the same guy. And this, because of the fact that this guy is at x and not at x equals 0, these also have this whole set of non-trivial poles. So I have, basically what I get is, if I call this whole thing, if I have a big bracket in this whole thing, what I get is just x times the same big bracket, and here I get x squared times the same big bracket. Okay, and then I have that for the higher order poles, and then I just have the usual J03 Vj x omega over z minus prime and J0 minus this guy. This, right? Again, here is a bunch of stuff I have no idea how it acts. This one, I know it acts as x dx plus h now. It's important that this is an h and not a j, because this is the actual spin of the representation in the zero mode sector, right? Otherwise, if this was on float, this would be the same as j, but it's not. And this guy acts as the usual x squared dx plus 2hx. And then I have regular. And then at some point, kind of an important thing is that, okay, this looks like a mess, right? A bunch of things I don't know. There are a lot of higher order code and so on. But the crucial, but is it kind of clear where this structure comes from? It's just the action of these higher order things here. These ones do not kill the state. And that means that as opposed to what would happen with an affine primary, I have extra points here. But the crucial observation from these people here is that although this looks very complicated, in particular I have a bunch of stuff I have no idea how to deal with, I have more constraints than usual. And I call these constraints, so these guys here, I could call them kind of unknown. Again, I have a formal expression for them, but nothing very useful. How many of them are there? There are, so from n equals 1 to n equals omega minus 1. Those are the ones I don't know, right? So if I'm looking at a correlator, for example, and I want to insert some current like this, it would be 1, omega 1, be n with omega n. Let's do 3-point functions, for example. How many unknowns do I get from inserting a current in some correlator? I get something like the sum from 1 to 3 of omega I minus 1. These are all the things that if I just insert some current in some correlator and try to use the OPE, I get a bunch of things I don't know how to do. But the key comment is that there are extra constraints.
An idea was you want to use these OPs to get some differential equations of the correlators.
Yeah.
Then you say this actually is not a differential equation because you don't know how to interpret these operators.
Yeah.
And now you will find a way
To go around it. And the extra constraint that I have is that I know that all of these modes are not killing my state, but I know that I have extra modes, which are these ones, but including the 0 if you, which are actually killing it. Right? Because you remember that I shifted the mode of J plus upwards, but I shift the mode of J minus downwards. Right? And these I can leverage into giving me more constraints on the actual OPs between the currents and the operator. And how does it happen? Well, I need to, since this is for a state in the M base, I need to kind of go to the M base, to the X base. But what happens is that if I build some current which is inserted at the same point in X as my operator, so I kind of take this whole expression, right, in terms of operators and translate everything into the X basis, right? So I get something like this, or some state like this, where it's important that these X's are the same, right? What is this thing that I'm building here? This is easy to define. This is just taking J minus and translating it to some point I just use the translation operator and I move it to some point x. But this I know how it acts because this is what it does. I know that the generator of the translation in x is just J0 plus. So I can use the commutators between J0 plus and the mode of G minus to get an actual expression for this thing, and it turns out to be just for this guy. It's just some combination of currents, which is J minus at the prime minus 2x J3 at the prime plus x squared J plus at the prime. Okay, if you want, this is just a definition. And if I take this particular combination and I put this inside here, right? And I play with, and I look at the OP with some guy at the same position in X, it's kind of clear where this comes from, right? I'm just translating in X. Just moving my, if you want M basis expression here, all together to some point in X. So if I look at this OP, then that tells me that not only do all the positive modes, etc., are annihilating the state, but also these negative ones. So if I take some huge combination of those three formulas that are there, you can see, for example, that what happens if I take, for example, let's look at the thing in brackets, right? If I look at the thing in brackets, I have to take the first one, then the second line and multiply it by minus 2x, and then the third line and multiply it by x squared, and then the bracket cancels, right? Because it was the same. It's this one minus 2x, this one plus x squared, this one. Okay, sorry, x squared, this one minus 2x, this one plus this one, and then everything cancels. But not only do the non-trivial poles cancel, this constraint tells me that I have a bunch of regular terms. So if I continue on this side, bunch more things are actually canceling. And what this should give me is that this should give me a bunch of zeros. So everything should be 0 until the order z minus z prime to the omega minus 1. This is the first, this is a very, for omega larger than 2, for example, this is a really a regular term that normally I wouldn't write in the OPE. But everything that comes before has to vanish. And then here I get the first non-trivial term. Sorry, this is minus omega minus 1. And the first non-trivial term I have is something like this. And then I have more regular, even more regular terms. So this is the first term that appears. But again, this guy, I know how it acts. Because this one is exactly the J0 tilde. Because I moved the mode in the other direction. So this whole thing has to be proportional to now shifting the h 1 unit down instead of up. Okay? Is it kind of clear how everything cancels? Yeah? Fine? Okay. Another question is, how do you actually use this to solve this thing? Because these are a bunch of constraints, and if you just try to do it at face value, you get just a bunch of, basically you get just a huge linear system of equations to solve for all of these guys that you don't know. And then on top of that, so this gives you two things. One, these constraints give you two things. One is a huge linear system of equations for all of these things that we don't know.
And this is not overdetermined, right? Because you get exactly the same number of unknowns and constraints because you've moved J plus and J minus, so the same quantity up and down. So,
Yeah.
But is it guaranteed that there's a solution?
Well, at the level of 3-point functions that have been solved exactly. 4-point function. So I think you can always show that the number of constraints is exactly the number of unknown things plus n conditions in an n-point function. Those n conditions are, that's what I'm going to write here. You get some system of equations to solve for this guy, and then you get plus n conditions. So this is for an n-point function. N extra conditions. Which involve two things. Differential operators in x, right? In the axis of each operator, because you have the action of the zero mode, which acts in this way, right? But it also involves recursion relations in the HI. Because in this whole system, you have a set of modes where the H's are shifted upwards by 1 or downwards by 1. Okay? And so the problem is that you need to write down the whole big system to solve for these guys in terms of primary correlators. Then you forget primary correlators. Then you forget about them because you already solved for them in terms of the primary correlators, and you are left with n conditions for an n-point function. And these extra conditions are those that actually allow you to solve for the primary correlators themselves. It's like when let me say it this way. I just said that the number of things I don't know, for example, in a 3-point function, is the sum of omega I minus 1. And what do I know? How many zeros do I have here? How many conditions do I have? Right? Because the fact that this guy is regular is no big constraint. But the fact that it has to be regular, it has to be 0 up to this order is a big constraint. So how many do you have? Well, the first one is z minus z prime to the 0. And the next one, z minus z prime to the 1, etc. until the z minus z prime to the omega minus 2. Okay? Okay? And in the end, what this gives you a sum over I equals 1 to 3, defined in 3-point function, of omega I condition.
Omega I minus 1, no?
No,
I thought you get the same, like, yeah, I'm trying to see.
no, because this one is fixed as well.
This one is also fixed.
This one is fixed because I know that it's in terms of some.
That's where the recursion relations come
Exactly.
in. Okay.
I have omega minus 1 here, and then one more here. It's an extra condition because this coefficient I know.
Yeah.
And then it gives me this number of constraints, which are n plus than the number of things I didn't know, and more than the number of things I didn't know.
This is an overdetermined system, right? To find your unknowns.
No, because because the set of things you want to find is this many things you don't know plus the primary correlator.
Yeah.
This is what you use to solve for them. But it's a mess. Problem is that it's a mess. I need to find an efficient way to actually deal with it. So it's not known how to. This is hard to do in general. So you need some kind of new trick to deal with it. This is where the relation to the actual choreographic theory comes into play. How much time do we have?
Sunset is at 50.
Okay, let's say. What I usually say, what this usually takes, I would say we have 10 minutes, something like that. Is that okay? Okay, so how to solve this? There are two insights here. So now it's where everything kind of comes together. One insight, so clue for solving this. So is the problem kind of clear? I have a big set of extra poles here. This gives me a big set of things that I don't know how to deal with. And I also have a big set of extra constraints. I need to kind of put all of that together in a simple way. There are two ways, two clues for how to deal with this. One is kind of technical. Is that I know that I would end up with a bunch of recursion relations in the edge. But this is very similar to what we already saw. Because when we did in the unflowed sector, we were looking at the M basis, not the X basis of operators. We had a bunch of recursion relations, right? This bunch of recursion relations was just the world identities in terms of the eigenvalues M, right? So the first clue is to trade recursion relations. So these are actually very similar to those for differential equations. Right? I need to find some new variable which allows me to write these relations as differential equations. And then it will probably be much simpler to solve it. This new variable I will call y, and it's going to be the conjugate variable to h. Right? So I'm going to define some new operator, which now I'm going to write as x, y, z. And I lost my h here because again, as before, I was losing my m in favor of the x. I'm losing the h in favor of the y. Okay, I'm going to define it properly in a second, but this is kind of the way you think about it. You just define some conjugate variable to h, which is a continuous variable, such that you can trade recursion relations for differential equations. Okay? The second way, which is kind of more physical if you want, yes.
So I thought X was already X is complete with M, right? And
Yeah.
then H is related to M also and omega, and you still have
This is the
It's not going to be a trivial sum.
no, it is, but this is the
one more variable now.
let me see. Now, once you have spectral flow, remember that I told you that you have states here, right? The original states which were horizontal now look like this. So for each value of little m,
Yeah, okay, so then you have to put M.
I have some x here.
Yeah, okay.
So what this y variable is going to do is going to resolve this whole thing, right? So not only moving here, which is x, but moving here is going to be y. Okay, so this guy is going to take everything in this kind of triangle.
If omega equals 0, it degenerates.
If omega equals 0, x is the same as y. Exactly. Yeah. This one. Okay. The second thing is that I know that the holographic CFT is related to symmetrical representation. To a symmetrical reference CFT. It's not exactly a symmetrical reference CFT, but it's sort of related to it. Kind of what I tried to argue in the introduction. And how do you compute correlators in a symmetrical reference CFT? Well, in a symmetrical reference CFT, what you do is you have a bunch of copies of the same theory. And in order to actually compute the correlators, what you use are some functions, which are called the holomorphic maps, which is you kind of, if you have some operator which is in some twisted sector of the theory, which kind of twists together, I don't know, omega copies of the theory. What I do is I go to a covering space, which is not the physical space in this boundary theory, in where these different copies of the theory are actually kind of the original theory in different little bits of this covering space. So I kind of trivialize the insertion of twist operators by going to some kind of covering space. So I want to do some kind of covering space of my boundary physical space, which what it does is it trivializes the insertion of all of the twist operators that I could have in a given correlation function. Okay? So if I have a correlator which looks like this, omega 1, omega 2, omega 3, for example, in x1, x2, x3. So this is kind of the simplest type of correlator you would compute in a theory. What this does is it changes the boundary conditions in your field. And in order to trivialize those boundary conditions, you go to a covering space. And going to a covering space is achieved by using some function to go from x to z, or the inverse if you want. You invent some function, gamma of z, such that for each z going to one of what in the worldsheet would be the insertion point, this behaves like the actual insertion point plus a bunch of things, bunch of orders that are not there, plus the first correction is something like this, where this is some numerical coefficient. And you want this type of behavior to be satisfied by all I equals 1 to n, well, in this case, 3. Okay? This is what's used, for example, in the Lunin-Matur construction. In the Lunin-Matur paper, what they do is they actually take computes, and you can do it explicitly, you can compute these functions in some cases and under some assumptions and so on. So for example, for 3-point functions at genus 0, at lowest order in large n, you can compute them exactly. And at the next order, I think, next orders, you can know a lot of properties about them. But you need to find some function which is holomorphic and which behaves in this way for all of the insertion points, plus x dot x, right? If you do, you can trade your correlator for a correlator in this Z space, where these things are just, if all I had here were just twist operators, now it's just some identities. So the correlator is just trivial to compute. The only thing you have to take into account is what it costs you to change coordinates from x to z, right? So you have to check what the conformal anomaly does to you when you use this map. But for the rest, for the actual problem of computing correlator, once you find this function, then you're done. Okay, just go on computing. That's what happens in symmetrical ripple theory. What we're gonna see, I'm kind of probably going to write the solution in the next lecture, is that you can use this function also in the worldsheet theory if you find it. Not only, even if the holographic CFT is not exactly a symmetric orbifold, if you find such function, you can use it to actually go and avoid all of these things altogether and find directly what the recursion relations are. And since you've already gone into the y variable, these recursion relations are not recursion relations, now they are differential equations. You can find those differential equations in general for 3-point functions, and you can solve them. And you can show explicitly how to compute this type of correlator, these 3-point functions, for arbitrary values of spectral flow, h, spin j, and all of the quantum numbers that are there. But you need to play with them in the correct way. And the reason why you need to have zeros in all of these terms here is exactly because when you play around with contours, contour integrals, and currents inserted in your correlators and so on, you need to avoid all of these annoying terms in DOPs. And what having these zeros here guarantees is that here you will use the action of the zero modes, say J A0. And this guy, because the first guy appears at order omega, is gonna pick up the action of the zero modes with a tilde. Right? It's gonna pick up the action of J plus omega, J 0, and J minus omega, which are the only things I actually know. And when you leverage all of this information, you can actually derive these differential equations in full generality. And you can explicitly see that in this way, so because this is not a symmetrical ripple theory, some of the worldsheet correlators exist even when this map is not there. You can show it. But what will happen when you go to the explicit tensionless limit is that all of those contributions go to zero. And the only thing that remains are the correlators where this map actually exists. And in that case, we'll see that what happens is that effectively, you see it when computing the correlators, the worldsheet itself becomes the covering map that you use when computing, becomes the covering space that you use when computing correlators in the symmetrical orbifold theory on the boundary. At larger values of k, so when you're not in a tensionless limit, it's a bit more subtle. The relation is not exactly the same because there's a deformation of a symmetric orbifold, but it still retains a lot of features of how you actually compute these things. And so this computation that I'm going to start with next time is going to give me the correlators of spectrally flowed states, even away from the tensionless limit. For the 3-point functions in particular, they are now known for any value of k, again, any value of omega, any value of h, of j, etc. But you need to actually go and find this type of functions. And these type of functions are very simple to compute. I'm not going to do it explicitly, but just to give you an example, and this is the last thing I write. If you look at a correlator where, for example, if I look at a correlator, let me say B1 with omega 1, B2, omega 2, B3, omega 3. If the set of charges that I choose is just 1, 1, 1, so 1 unit of spectral flow for each of them, then you look, there's a known recipe to compute this map, You just kind of leverage all you want from it, and you get the condition that ends up being telling you that this is a ratio of hypergeometric functions which have indices such that these are not infinite sums. These are like the ratio of polynomials, if you want. If I set the x is at 0, 1, and infinity, then the map for having 1, 1, 1 is just gamma of z equals z. Nothing very interesting to do. But if I do, for example, omega, omega 1, then my map is gamma of z equals z to the omega. And this starts looking a lot like what we did in the first lecture, right? Because in the first lecture we had some fun. We were looking at the for example, at what happened with the holomorphic fields. In the second lecture, if you want to do it in the Euclidean model, and I argued that for a long string solution, I had the classical result for my gamma. So the classical solution to the equation of motion was z to the omega. So what will end up happening is that this function here, this covering map, will end up related to the expectation value of this gamma here, which again is a map from the worldsheet to the boundary. Okay? And then you can get more complicated things. Just to give you a non-trivial example. Where did I write it? If you take omega being 3, 3, 3, then gamma is some function which looks like that q minus z over qz minus 1. You compute it's some function. This function has a property that it behaves in this way near 0, 1, and infinity, with omega being 3. In our case, you can just expand around each of these points and you find it, and it works this way. There are no near 0, this is going to behave like z cubed. Near 1, it's going to behave like 1 plus something times z minus 1 to the cube, and so on. And these are the kind of things you use to actually go and compute your correlate. And that's okay. There's no, I finished all the technical things. That's all for today.
Yeah, sorry, the z minus zi to omega, zi is xi. Am I wrong?
No. So if I have, you remember I have, so this.
In the gamma expression. The gamma expression. The last term is z minus xi.
No. For each insertion, right? I have some quantum numbers, etc. But then I have two complex coordinates. One is x, and one is z.
Okay.
X is the one that appears here, and z is the one that appears here. If I'm near this guy, so near the gamma goes from z to x. Near this guy, I get x plus some correction, which comes only at an order which is fixed by the vector flow.
This is the space-time CFT coordinate.
Right. But the magical thing is that you don't need to know anything about symmetric orbitals. I mean, you could have found this just as a trick to actually go and compute these correlators. But then you realize that this is exactly what you use in symmetric orbitals to compute correlation functions. And this is a clue, and then I don't know how general it is, but it's a clue of how, at least in the AdS3 CFT2 case, how holography is actually working. And it's really relating in a non-trivial way the worldsheet of the string and the boundary of AdS through these maps. That's exact in the case of the tensionless strings, and it has some corrections away from that. But but this is how it kind of works. This is what allows you to forget about, to avoid all of these terms, complicated terms in the OPEs that you don't know how to deal with.
Does the covering map has any like M-basis interpretation or?
The M-based interpretation is this one. It's the explanation value of this guy. You can go into kind of the Wakimoto fields language, the free field language, and you can see that if you have some correlation function which is non-zero, for example in the tensionless string case, which is non-zero, there is a covering map. Then you get some expression for the correlation function. But if you take the same correlation function, what I'm gonna do is that we compute this guy, V1, V2, V3, right? That'll give you some. Then you compute, it gives you some function f of all of the variables. Then you try to compute what this guy is, and you do it in the free field, this guy instead, and you do it in the free field limit, where this guy is actually holomorphic. And by free field, I don't only mean, I mean treating the theory in perturbation theory in the interaction term. And then what you get is this. That's a more physical interpretation I know. And how this actually works is it has some interesting subtleties and it's actually very nice. I probably won't have time to do it, all of it here, but it's in the notes. It's in the notes in the section of the notationless string section. Other than that, well, yes, another interpretation you have for this is that, so I don't know how much, because again, I cannot do everything. It's in the, if you remember a bit about symmetric orbifolds, or if you ever read anything about it, you know that if you're in twisted sectors, you have fractional modes, for example, for the curve. In a twisted sector, which is, let's say, labeled by omega, then, for example, the Villatoro modes that usually have n integer, now n, you have modes which are in integer divided by omega, right? This map is the change of coordinates between being in one and the other, being in the untwisted sector and the twisted sector, and create having this mode.
Right, but that's because it's the map. I mean, as you said, it's the map that untwists you and like, lets you. Yeah, it's the covering.
But you can write, so n basis is just a basis of mode in the holographic theory. That's the only thing it does. It takes your local operators in the boundary and it expands them in terms of mode.
I'm asking because, like, here, as you said, like, this is the way of how AdS3 works, because you see the world sheet, it maps to the like, but this is very, like, 2D, 2D, right? Like, so if I want to generalize this, and I don't want to think of X as some 2D coordinate, or like, it feels like the M basis would generalize more easily to other dimensions.
Yeah.
In which case, I would like to think of all of this technology more in this M basis than having just a CFT2. That's easy.
Except for looking at, in this paper about black hole microsites, for example, and so on, we were using all of this to try to working in the M basis because that was more natural for this particular site. And then again, this trick was just to kind of defining the fractional modes in the boundary from the worldsheet perspective. That's what it's doing for you. Maybe some more interesting answer directly to what you're saying, but we can discuss more about it. I think that's much more precise. Okay. Then next time I write the solution to this, and we go into the holographic theory. We go into the tensionless string.
Next time is on Friday at 10 o'clock.